Welcome to this important lecture on separation principle. We will present a controller estimator combination. We will explain what is meant by separation principle. Let's recall what we have seen so far. We designed a pole placement controller using Ackermann's formula. We also designed an estimator when not all states are measured. This is known as the duality principle, and the estimator designed in this method is known as the Leuenberger observer. A schematic is in the next slide. So here is the schematic. We have the plant here. The plant has states X, but X is not measured. We have a sensor indicated by C. What is measured is indicated by Y. That Y goes into the estimator block. Out of that comes X bar. Our feedback control law is known as K, U equals minus Kx, but in the place of X we put X bar and that is U. So this is the controller estimator combination. X is not measured, Y is the measurement, X bar is an estimate of X, and X bar is used in the feedback controller, U equals minus Kx bar. Now we explain what is meant by separation principle. Assume that the states are available and design controller K. We design K without worrying about whether the states are available. Note that the control law formula has only A and B. Similarly, we assume that the states are bounded and design an estimator LP. If the states are not bounded, it doesn't make sense to estimate them. So we have to make assumption that the states are bounded, but the states will not be bounded if there is no good controller. So here we assume that the controller is already designed and in place and go on to design LP. While designing K, we assume that the states are available, that is an estimator is already available and so we can use that and so on. So we design this K and LP in parallel, assuming the existence of the other quantity. This is known as the separation principle. This was proved by Kalman, who showed that you can do this in parallel and put them together and the system will work. It is a very important principle. It made the controller design a lot easier. Designing both of these simultaneously is a lot more difficult problem. Alright, let us look at another aspect of the conventional controller. Notice that the blocks within the dotted lines make up the conventional controller. The input to the dotted lines is Y, plant output, and the output from there is the control law U, which goes to the plant. So this whole thing is equivalent of our conventional controller that we designed earlier on. Now let us calculate this conventional controller. Here is our estimator equation and here is the control law that we will actually implement. Notice that it uses X bar, the estimate. Let us close the loop. What is meant by closing the loop? Notice that a signal comes back from here back to this. So let us put that in the place of U here, we will have to put minus Kx bar. That is what is meant by closing the loop. So let us group all the X bar terms. We get this A minus Bk minus LPC. Notice that for the pole placement controller we had A minus Bk, for the estimator we had A minus LP, but now we have a completely different term that has both Bk and LPC. So what are the implications? It will become clear shortly. Next question, what is the dimension of X bar? You can see that it is the same as that of A, that is, it has dimension n. Let us derive this controller, conventional controller. So we derived this expression in the last slide. Let us assume the initial state to be 0 and take Z transform, bring this term to the left hand side and we get this expression, and take this matrix to the right hand side, which can be substituted in the expression for u equals k into x bar. So this is k into x bar, this whole thing. So this is the conventional controller, the input to that is y, plant output, and the controller output is u. It has this A minus Bk minus LPC as we mentioned earlier. We will present a numerical example now. We have A, B, C. This system is something that we have already seen before. We can check that this system is controllable and also observable. We will design the controller for closed loop poles given here. This is the same set that we used earlier, and notice that this will result in this alpha C, and we can calculate this, and we can calculate k to be 0.5 and 3.5. We have already seen this example in an earlier lecture. Now suppose that we want to design an estimator with poles at 0.1 plus minus j times 0.1. You can notice that these poles are lot closer to the origin as compared to the controller poles. As a result, the estimator is lot faster. So normally we choose estimator poles to be lot faster. So the control law uses the correct estimates of the state. So we have taken the estimator poles a lot closer to the origin. So with this we get this alpha E as given here. You can evaluate alpha E of A because we want to use Ackermann's formula to arrive at LP. So let us calculate alpha E of A. If you simplify this, you will get this expression, and you can also calculate script O, which has C and CA, to be this 2 by 2 matrix, which is also non-singular, and hence you can find its inverse. And using the Ackermann's formula for LP given here, we can calculate LP as given here. So it has 3.8 and 4.21. These are the values we saw in the previous slide. Now let us use the conventional controller. Remember the expression we derived for U. From there we get this conventional controller GC as given here. And I have calculated A minus Bk minus LPC using this A, B, C, K and LP. By substituting here I get this. Then we substitute it here and calculate GC. For that we find the inverse first, and then it is seen to be this. So the value for GC can easily be calculated to be this term given here. I would want you to go through this, calculate every step, ensure that you get this last term. Let us analyze this controller, which we obtained using pole placement technique and using an estimator, but we have presented it in the form of a conventional controller. This is what I have been meaning by the expression conventional controller. Notice that the controller order equals dimension of A, and the dimension of A is 2 here. A is a 2 by 2 matrix. You can also notice an important property of this controller, that GC is unstable. You can see that the zeros of the denominator are outside the unit circle. In other words, GC's poles are outside the unit circle. So GC is unstable. Even though controller and estimator are individually unstable. Remember how we designed the pole placement controller? We chose K so that A minus BK is well behaved. Then we designed the estimator by making A minus LPC well behaved. These two individually are well behaved, but after putting them together, there is no guarantee that it will be stable. As a matter of fact, we have seen the example where this GC is unstable. I have the Scilab code for this. I would ask you to go through this, execute this, and identify different things that we have done in this lecture. To conclude, we have derived a combined controller and estimator. We presented the important separation principle. Although the controller and the estimator are individually stable, the combination could be unstable. We presented an example. We also showed a Scilab code. More state space techniques will be covered in subsequent videos. With this, I have come to the end of this presentation. Thanks for joining. Goodbye.